Right. So we continue with the hypothesis testing. So you are given this question to suppose that an archaeologist. Hello?
Hello? I'm
Yes.
unable to see the screen.
Oh, you can't see the screen. What should I advise? Try to log out, log in.
Okay.
Oh, so given this question and an exercise, you are to suppose that an archaeologist discovers only 7 fossil skeletons from a previously unknown species of miniature horse. So reconstructions of the skeletons of these 7 miniature horses show the shoulder heights in centimeters, and these are the shoulder heights in centimeters of the skeletons. 1, 2, 3, 4, 5, 6, 7. So in short, the sample size of the skeletons are how many? They are 7 in number. Is that right? And then you are given that from these sample data, the X bar, the mean, I said that the mean from the sample is called what? X bar. Is that clear?
Yes.
The X bar is the mean from the sample. It is given to be 46.14, and the sample, the standard deviation has been given as 1.9. I'm hoping that you have a calculator today. Is that right?
Yes. Yes, I have.
Okay. So now we are asked to find a 99 confidence interval for mu, which is the population mean. So we are, in short, we are constructing the what? The confidence interval. And I said how to construct the confidence interval. The first thing that you ask yourself is that what variables are we dealing with? What parameters are we given? Are they the mean? Are we given the mean and question, the average? If you are given the average, then your confidence interval shall start with X bar because you're dealing with the mean, right? But if you're dealing with the proportions, it will start with P bar, like you're looking for proportions. That is what that means. Then the other thing that should guide you on how to proceed is the sample size. I said that you have to examine, is the sample size big or small, right? If the sample size is small, it means you need to use the T statistic. Is it not what we say?
Yes.
We need to use the T statistics. And if the sample size is big, we need to use the Z statistic, isn't it?
Yes.
So in this case, what statistic are we using?
Isn't that T?
Yeah, so we use the T statistic because the sample size is less than 37. And so since it's the T statistics, T critical value divided by 2, N minus 1, this will give us the critical value of T, right? Multiplied by the standard deviation, S, small s in this case, over the square root of what? Of N, right? Is it what we said last time? Yes, that is what we said. And so from there, we will have to put the numbers. X bar is what? 46.14 plus or minus this value here. This is a figure that we get from the table, right? We get this figure from the table, isn't it? We get this figure from the table. In this case, since we're using the T statistics, we get this figure from the T statistic table or the T distribution table. So in the meantime, we pause about it. We know that there is alpha here. The alpha is the level of significance. So we are told that the level of confidence, the confidence interval level that we are using is 99, which means what is the level of alpha, the level of significance? Hello?
Yeah. Hello?
Yes. Yeah. So when you add the level of confidence or the confidence interval level which is 99%, plus the significance level, they should give you 100%. You get. So if the confidence
So
interval
it's
level is
1.
99, yes, it's 1%. So your
1,
alpha
1%.
is 1%. Yeah. So your
Mhm.
alpha is equal to 1%, which is same as
1%.
0.01. Is it?
Yes.
1% is same as 0.01. Right. And this is a table-tailed, so we are dividing this by 2. What do you find as the level of alpha?
Mm, 5. It's giving 5. I don't know why it's giving 5 to the power negative 0.3.
Okay, so there are 3 decimal places after 5. So that is 0.005. It is 5 times 10 to the power negative 3, right?
Yes, yes.
Yeah, so that is the number. So that number, comma the degrees of freedom. I said n minus 1 is the degrees of freedom. Our n is 7, the sample size, minus 1 giving us what? 6, isn't it? So the degrees of freedom are how many? They are 6. You get the point, eh? N minus 1, yeah, the sample size, minus 1. So this number now is the number that we are going to use to the what? To the table. Using the Z statistic table, it will give us this degree of freedom, comma, this alpha level. They will give us the critical value to put there and multiply it with what? That value to be multiplied by the standard deviation, which is 1.19 divided by the square root of what? Of 7. This is to be treated as one number.
Oh, okay.
So just say 1.19 divided by the square root of 7.
So 0.676.
Sorry?
0.676.
0.676.
765.
Okay, like this? Okay. So that is what we get on the last parameter. Then let's look at now this number which is here that I've left. This one we get it from the Z table. So you have to look for where the degrees of freedom is 6, right? Degrees of freedom is 6, comma, where alpha is 0.05, isn't it?
Yeah.
What is 0.05? It is 1%. It is 0.05. It will just be 0.05%, just like that. Because we have divided it by 2, it's no longer 1%.
Yes.
So we go to the, let's go to the, keep these numbers, right? You're keeping the numbers somewhere, right?
Sure, there's 0.
Hello?
Hello, yes, I can hear you.
You have kept these numbers?
Yes.
Okay, let's go to the table. We are looking for 0.05 degrees of freedom, you see, 6. We go to the table that will help us find the, there should be a table to help us. There should be a table to help us find the level of alpha. It's a T distribution, right? This is the chi-square distribution. We'll use it very soon. The T distribution, this is the standard normal distribution to the right. Do we have the T distribution? It should be there. The chi-square Where is it? Yeah, here is the T distribution. Have you seen it? It is labeled. Have you seen the T distribution table?
Yes, I've seen it.
I tried to zoom. So the degrees of freedom are here, DF. You said the degrees of freedom is what? Is 6, right?
Yes.
Mm-hmm. 6. What is our alpha? For 0. What?
It's 0.05. 0.05.
0.05.
Yes.
Like this one, because this is 0.05.
Yes. You said 1 divided by 2. Yes.
Or it was 0.005.
Yes.
It was 5 times 10 to the power 3 negative, right? It means the point moved from here. 1, 2, 3. So the
3
point is somewhere.
okay.
So you see here.
0.005.
Yeah. So the critical T is which one? It's this one, right? So that's the value. So it was X bar plus or minus the T statistic, comma N minus 1 multiplied by the standard deviation over the square root of what? N, right? So what was the X bar? It was 46.14 plus or minus this part. Now we have found it, isn't it? It is 3.707. You're following?
Yes.
Hello?
Yes,
Yeah,
I'm
so this
following.
part, the whole part of this is one number. It's the one number that you get from the degrees of freedom, this, comma, the alpha level, which is that number you have found. Then everything multiplied by what now? What number did you find here? Standard deviation over the square root of N. So
0.67. 0.67. 65.
Okay.
6765.
All right. Like that. So far, is there any question?
No.
Question there is no. So in short, know where you find the degrees of freedom at this line. Then you just check the levels of alpha. They are all here. Yeah. Whatever alpha you can calculate here, then just check where they intersect, That's how you get the critical value. If you're using the T distribution, not the Z. The Z one is not a big deal. You learn that under standard distribution. So you can have 46.14 plus or minus 3.707 multiplied by 0.6765. So now, what you do, find one number here. You got to find one number here, multiply these two. This part, we call it the margin of error, okay? That I've circled, this margin of error. It's X bar or minus the margin of error. The whole lot of that part is the margin of error. So what is the margin of error? This is 3.707 times
0. 0.66765. 2.50077.
2.5077, like this, plus or minus. So when you want to get the upper limit, you add. The upper limit in the confidence level will be 46.14 plus what? 2.5077. And then the lower limit will be the same, but you subtract, right? Minus 2. 5077. So this is how you create the confidence interval. You get, so subtract this side, you find one number. You subtract, you find one number here. This is the upper limit, this is the lower limit. And now, so the thing is that you have to check if the mu, which is the hypothesized value, right? The mean from the population is within this what? This range, okay, this interval. If it is within the interval, you fail to reject the null hypothesis. You get the point?
Yes.
If it is within the interval. But if it's outside the interval, you reject the what? The null hypothesis. You got it? Any question? Do you get the question?
So how do I tell if it's within the range?
Oh, let's assume, because in your question they didn't give mu. Let us assume that mu, which is the mean from the population, maybe it is in this case 55, right? And your standard deviation was, the lower limit was 46 minus 2 something, so it should be 44 point maybe 0 something, isn't it? The lower limit. Then the upper limit is 46 plus 2 something, so it will be somewhere around 49 point maybe 07, isn't it? So you just take this 55. Is 55 within this range? Is it falling within this, between these two numbers?
Oh, okay. Yes. Oh, okay. So
if it's outside, you reject the null hypothesis. That is to say, you are rejecting that the statement is true. You get the point, eh? I gave you previously that example of the first year student. I said their mean age is 19. It's 19 years. Then you sample and you test the hypothesis. If you find that the mean age, this one from the population, the mu is not equal, is outside this the range or the interval, then you reject the null hypothesis. That is, you are saying that no, the mean age is not 19. That's what it means to reject. But if you fail to reject, if it's within the range, you fail to reject the null hypothesis, meaning you are agreeing that the mean age is 19. You got it? You okay?
Yes, I'm okay.
Now let us change now the parameters a bit for you. Let's change the figures a bit so that you also realize when the sample size changes. What if we are using the same? The X bar is still 46.14. Follow. The standard deviation is still 1.19, but the sample size now is 36. Have you seen the changes?
Yes.
And then alpha is now 5%. Or the confidence level is 99%. So I have to understand, when they say confidence level is 99%, then alpha should be 5%. Usually these are numbers less than 10. They just go 1%, 5%, the common ones use, and 10%.
Oh, okay.
Which means if it's 10% level of significance, then the confidence level will be what? Will be 90. Yeah, so I have to understand that. So let's try to do this one. What statistic are we going to use in this case? What statistic are we going to use?
The Z.
Yeah, so you use the Z statistic because the sample size is now big. So X bar plus or minus Z statistics alpha over 2 multiplied by the standard deviation over the square root of n, like that. The mean is still 46.14 plus or minus. You go to the table, the Z table, to find this one. You know how we find this one from the table. Let me just remind you. Our alpha is 5%, which is same as what? 0.05, right?
Yes, 0.05.
Then we divide that by 2. And what do you get? What do you get?
0.05 0.025.
So 0.025. This is the level of alpha that we are looking for, multiplied by standard deviation, which is 1.19 divided by what? The square root of 36, which is 6. So you can say 1.19 divided by the square root of 36. And what do you get?
1.19 divided by square root 0.1983.
So 0.1983 is to be multiplied by. Now we have to get the critical value here because this is not the critical value. So since we are using the Z statistics, you have to go to the Z table. You understand? Go to the Z table and look for the area that corresponds to 0.025.
Yes.
So you go to the Z table. Finally, you have found the Z table already. And this Z table, it already gives you the areas that are on the alpha, isn't it? You know that alpha sits it sits after the Z value, isn't it? So this area, this table already gives you the levels of alpha. So we are looking for that value, 0.025. In which line do you think we can find the number 0.025? Are you able to locate it?
Nope. I've seen 0.0250.
Which line?
Yeah.
Which
Where
row?
there's 1.9.
1.9. What is the column?
This one here, 0.6.
0.06. So
I don't know if it's the
it
one.
means yeah. So you get 1.9 plus 0.06. You add. This will give you 1.96. Is it?
Oh, okay. So
now this is the number that you put here. 1.96. I'm just trying to re-echo what we did last time so that you can understand. So what is the margin of error?
Okay, so 1.96. Is it multiplied by 1? We multiply these two, right?
Yeah, these two you have to multiply them.
1.96 times 0.93. 0.3886.
0.3886.
Yes.
Yes. So when you want to find the upper limit, you add the margin of error.
Okay.
And if you want the lower limit, you subtract the margin of error. So basically, this is your confidence interval using the Z statistic. And then you test the hypothesis. How does that sound? That's easy, right?
When you reach this stage, it's easy. But where it's tricky is for me, how to tell where to use the Z statistics and the T statistics.
No, I said you look at the sample size.
Oh, the
It's to look at
size.
the
Oh,
sample size.
if it's small, oh, okay.
If it's a small size, you
The
you use the
T
t-statistic.
statistic.
Then
If
the
it's
z
big,
is
the
for the
Z.
big size.
So now, how to tell if the sample is big or small? So I need the examples.
How to
Or
tell if the
using
sample is big is to look at the number. Is the number in question greater than 30? Every sample that is 30 and above, that's a big sample. As
Oh,
long as the
okay.
sample size is 30 and above,
30 and above. Oh, okay.
that's large sample. You use Z statistics. If it's less than 30,
Use
29
T.
coming down, use the T statistic.
Oh, okay.
Some more
Okay.
questions?
No, that's okay.
You're fine?
Yes, I'm fine.
Is this hard? No. It isn't it?
Not.
Yeah, so basically that is about the use of the T statistic in hypothesis testing. I'm trying to go over them. I know, like I've done so much work on T statistics, how to use now the T, because this is confidence interval that we are doing, right?
Yes.
Yes, this is confidence interval method. Okay. The confidence interval method. Then we'll use now the Z statistic only, not the confidence interval method. How do you use the Z statistic to test the hypothesis, and how do you use the T statistic, to test the hypothesis? And when I share those recordings, please be faithful to follow.
Okay. All right.
Yeah. Okay. Let's go. Yeah, this is we have done this example already. Actually, we tried it to. Yeah, I've done this one, isn't it?
Yes.
Now, the other thing that you need to learn is the idea of stating the hypothesis. How do you state the hypothesis? You know, our first step actually to establish the working hypothesis about the population parameter is a question. So the hypothesis is called the null hypothesis. That is actually denoted by H naught. So the value specified in the null hypothesis is often a historical value or a claim or any other specification or hypothesized value. Some words I'm saying are not in the notes, if you're following. Yeah. So it is called the hypothesized value. So that existing claim. Last time I wanted to make mention of this. Yeah, just trying to give you the example that you can easily relate with. Let's say a television networks claim that the average, which is mean, right? The word average means mean. So the average length of time devoted to commercials in a 60-minute program is what? 12 minutes,
12
right?
minutes.
So the average, which means the mean. In this case, the mean which is existing in the claim is called the mu. So in case your mu is what? Is 12, right? So your null hypothesis will be such that mu is equal to what? 12 minutes. You get the point, eh? That is how you state your null hypothesis. Mu is 12, which means that the other hypothesis, which is the alternative hypothesis, will be mu is not equal to what? To 12. There should be the other claim. Remember, I told you when you say the statement, there will be other researchers who are coming to test. Those people who are testing, they have to formulate a question against a claim that is against the existing claim. So that claim which is against is what is known as an alternative hypothesis. How does that sound? Okay. Now, imagine that one I was saying, the average age of the first year student is what? Is 19%, is 19 years old.
19
right?
years, yes. Mhm.
That's a claim. That's the first claim. Then someone is skeptical about that and wants to test this claim. So first of all, the null hypothesis will be what? The null hypothesis will be such that mu is equal to what? To 19. Then the
19.
alternative hypothesis will be such that mu is not equal to what? To 19.
19.
That is very, very important for you to understand about how we form the hypothesis or the questions. Now, any hypothesis that differs from the null hypothesis is called an alternative hypothesis. I've gone before the slides.
Yes.
I've said this already. Yeah.
Yes.
So basically, that is what is happening. And now, let's say if you believe that the average length of time devoted to commercials in a 60-minute program is lower than the television, okay, then it means that, you know, your alternative hypothesis will be less than that. For example, the mean is said to be what? 12, right? So the null hypothesis will be such that mu is equal to what? To 12 minutes, isn't it?
12, yes.
Then the alternative hypothesis, you are believing that it is what? Is longer, which means it's more than
yes.
what?
More than
12 minutes.
12.
So it means your alternative hypothesis will be such that mu is greater than what? 12. Have you seen how different it is now, how you form that? So you follow the words. If you believe it's less, then here you will put less.
Less, okay.
Or maybe sometimes they may not use these common words that you know, less, more. They can say, if you believe that the claim exaggerates,
Or
you get the point.
meaning it's greater.
Yeah, so
right?
it means that if they say it exaggerates, meaning it is putting too much, like they have said the average is 12, that's too much. So, which means you believe that it is less. You get the point?
Oh, okay. Yeah.
That the first claim is exaggerating, meaning it is, you know, yeah, you get the point. So your belief shall be less. If you believe that the first claim is understating or undermining, then you have to, your alternative will be great. Because if it is understating, which means you believe that that's less, which means it should be more than, you get the point. If the null hypothesis is 12 and you believe that this 12 is an understatement, you get the point, or an underestimation, which means your belief, it is logic for us to say you believe that it is more than that. If you're complaining, no, this is too little, meaning you believe that it should have been more, right? Are you fine with the issue of forming the hypothesis?
Yes.
And this now should answer a question that usually most of the students, actually almost all the students I taught hypothesis testing, they asked me, and they were saying, so how do you tell whether the data set is double-tailed or what?
Yes.
Or single-tailed? You're also asking the same question. Yeah, so it is just this same formation as well. So if you see your alternative hypothesis is less, it shows that the data is tilted to the left, to the negative side. So it's single-tailed. In this case, this data is moving like this. It's single-tailed from 0 going to the left like that. So it means that your alpha, when you have your alpha, the level of significance, you don't have to divide it by 2. You get the point?
Yes.
If you're given the alpha, you don't have to divide it by 2 because the data set is single-tailed. You got it? Then if your alternative hypothesis is greater, it means that the data set is single-tailed, tilted to the right. It is skewed to the right. Yeah, if you remember the level of skewness, I talked about the issue of skewness, ketosis.
Rightly skewed.
Yeah. So if you believe that the mu is greater, it means that this data set falls to the right, is right skewed. So for that reason, it has a longer tail to the right, as compared to anywhere. So, which means that it is single-tailed. But if the mu is not equal, it means now, if it's not equal, it can fall either to the right or to the
Or
what?
to the
To the left. In that case, what do we say? It is double-tailed, right? If it can fall either to the negative or the positive side, then the data set is symmetric like this. It follows the normal distribution, right? Any question?
No.
So the question has been answered. How do you tell whether you have to divide the alpha or you don't have to? This is the question. You divide the alpha when it is double-tailed, but if it's single-tailed, you don't divide the alpha.
Okay.
Okay. So the null hypothesis is the statement that is under investigation, all right? Or the statement that is being tested. Usually the null hypothesis represents a statement of no effect or no difference. Yeah. Or put another way, things haven't changed yet. Like it is just like that. Like that's the original claim or the existing claim. That's a null hypothesis. Whereas an alternative hypothesis, the one that you are going to adopt in the situation is actually a statistical test that is designed to assess the strength of the evidence against the null hypothesis. That is an alternative hypothesis. You get it? It's a statistical test that is designed to assess the viability, the strength of the evidence against the what? The null hypothesis. Okay? So in short, in other words, the alternative hypothesis is there to, to rule out the null hypothesis. Okay? Any question?
Yes. No.
Okay. Now, let's try to test the understanding. A car manufacturer advertises that the new compact model, they get 47 kilometers per liter. Okay, these are manufacturers of the car. Now, let mu be the mean of the mileage distribution for these cars. So you assume that the manufacturer will not underrate the car, but you suspect that the mileage might be overrated, isn't it? So follow nicely. We need to state the null hypothesis, and you're going to state it. Number one, a car manufacturer advertises that the new compact models get 47 kilometers per liter. You get? So let you be the mean or the mean of the mileage distribution. In short, you are saying that on average, the mean or the mu is what? 47. This is what they are telling us. The manufacturer is saying, on average, it takes 47 kilometers per liter, right? That's what the manufacturer is saying. Now, you, in your assumption as a researcher now, you assume that the manufacturer may never underrate the car. You get the point? Like when he's the owner, he's the one who is making, he may never underrate all the time. But instead, you suspect that he may overrate instead of underrating. Now, can you state the null hypothesis and an alternative hypothesis? What would be the null hypothesis? H0.
The null is not 47 kilometers per liter.
So you are saying the mean is 47?
Hello? So. Hello?
So mu is equal to 47. What is the
47.
alternative hypothesis?
U is greater. Is
Follow
it?
the language. You assume that the manufacturer will not underrate the car,
Oh, less.
but you suspect that the mileage might be overrated, meaning rated more than necessary. So meaning you believe that it is what? It's less.
Less, yes.
Yeah. Is that clear?
Yes.
Any question? So basically, that's how you form the hypothesis. You don't even suffer. These things are very easy. No need of
To
suffering.
understand the language.
Yeah. Now, the now hypothesis always states that the parameter of interest equals a specified value. You get the point? This is very important for you to take home. The now hypothesis always states that the parameter of interest equals a specified value. The alternative hypothesis states that the parameter is less than, is greater than, or simply not equal to the same value. Have you gotten that one? You didn't get it. I'll repeat. When it comes to the now hypothesis will always state that the value is equal. Okay, that is what you have already. But the alternative may be less than, it may be greater than, or not equal.
Oh, not equal to. Oh, okay.
Those are possibilities. So you have to listen carefully to the formation of the alternative hypothesis. So we will categorize the statistical test as left-tailed, that's less than, left-tailed. Right-tailed, that is greater than. And the two-tailed, meaning double-tailed, not equal. If the alternative hypothesis is not equal. I went before these notes, if you followed.
Yeah.
Yeah. So that is what is there. Maybe just to over amplify and still say the same thing. So left-tailed, if the alternative hypothesis said that the parameter is less than, that is left-tailed. Right-tailed is when the parameter is greater than. Double-tailed is when the parameter is not equal to. You get the point? We have explained now what it means to be two-tailed or double-tailed, right?
Yeah.
And less-tailed, single-tailed. Is there any question?
No question.
Trying to teach you the language. Coming are the nice days ahead of us. Don't worry. Now, in inferential statistics, we test the now hypothesis. So, you know, a hypothesis is a statement of an expected relationship between the variables, okay? That is called a hypothesis. Trying to define what a hypothesis is, you know, it's a claim, okay? The statement of the expected relationship between the two variables, right? Yeah, that is what the now hypothesis is all about. So now, can you suppose that a principal wants to cut down on absenteeism in her school, you know, and orders an incentive program for perfect attendance? So before the program, can you suppose that the attendance rate was 85%, right? It was 85% before the program. After having the new program in place for a while, she wants to know what the current rate is. So she takes a sample of days and estimates the current attendance rate to be what? 88%. So the average has increased now to 88%. This is what has found. Now, the researcher hypothesis is the attendance rate has gone up since the announcement of the new program. That is an alternative hypothesis. You get the point, right? Then the null hypothesis will be that the attendance has not gone up since the announcement of the new program, meaning things are still like it's equal, like it is just like that. Have you gotten the point?
No.
Yeah, you haven't. I'll repeat. We want to show you how to form the hypothesis in this case.
Yes.
There is this principle. They want to cut down on absenteeism in the class.
Yes.
And so for that, they order an incentive for perfect attendance. Before the program, what existed, the situation that existed was that the attendance rate was what? Was 85%. That is the existing statement. Like, that's the claim which is there, existing. Now, what you're going to do as a researcher, you're going to test if we make adjustment, this value will change or will not change. You get the point? Yes. So the null hypothesis will be that no, the value will not what? Will not change. Meaning the value is like this. That is mu is equal to that. Then the alternative will be no, mu is not equal to that, which means when we make changes, the value that we find will not be equal to that. You get the point? Yes. So now, after that, so they sample, they do a sample, they calculate, they find that the rate is now 88%. So the null hypothesis, of the researcher will be that the attendance rate has gone up since the announcement of the new program. That will be the alternative hypothesis. Like you are trying to say that after the changes, there was a change in the what? In the attendance. But the null hypothesis is saying that there was no change, isn't it? Yeah. With the null hypothesis, you're saying that there was no what? There was no change. No change. Right. Now, so the research, then the null hypothesis is that there was no change, but the alternative is that there was a what? There was a change. So basically, that's how one would form this what? The hypothesis. Is that right? So when you look at it, it seems that the null hypothesis is wrong, right? 88% is greater than 85. But since we are using a sample, it is possible that the true population value is less than 85. It's possible. Very much possible. Since it's just the sample that we are using and it is just a representation. Okay? So based on the sample, how likely is it that the true population value is less than 85? That is what we are trying to investigate. And if the likelihood is more, then we say our null hypothesis is wrong. Right? Then we reject our what? Our null hypothesis. But if the likelihood is reasonable, then we fail to reject the null hypothesis. Yeah, which is just almost the same language that I have been commenting on severally. And so now you have this good example. So the drug 6-MP6 is used to treat leukemia. So the following data represents the remission times for a random sample of 21 patients using the 6-MP. Okay, right. So this is the sample that was gotten. We want to look at the impact of the drug, right? There are 21 people, the random sample of 21. First of all, the sample size that we are using is 21. It's a small sample size. Are you able to follow that? It is a small sample size, 21. So we need to test the hypothesis. Let's see what happens. So after calculating, they found that the mean is what? Is 17, right? You following? Yes. The X bar in this case, X bar is what? 17. Is 17. Then the standard deviation is what? Is 10. Yeah. And it is said that the drug treatment had a mean remission time of what? Mu. Our mu is what now? 12.5.
12.5.
Do the data indicate that the mean remission time using the drug is different from 12.5%? Use alpha 0.01. Okay. Does the data indicate that the remission time using the drug is different? Yes or no? Is it different? So you assume that you believe that the time is what? Is more, right? In your belief, you believe that the time is more. So you use your alpha, which is equal to 1, right? In this case. So your mu is equal to what? 12.5. First of all, we estate the null hypothesis. Then alternative mu is not equal to what? To 12.5. Means that this is a double tail. For that reason, this alpha, which is 0.01, shall be divided by 2, giving us 0. What? You had found 0.005. Is it? Yes. This is what you had found. You had found 0.005. So we need to create the confidence interval to test. Okay. How do you create the confidence interval? It is x bar plus minus. This is a small sample. Have you seen that this is a small sample? You're dealing with the statistic. 21. Yes. So it's a t statistic. So t statistic, comma degrees of freedom 1, comma the standard deviation is 10 over the square root of 21. Right. Okay. So what is our x bar is 17. Okay. Plus or minus. What was our alpha? I think the alpha, the degrees of freedom are different now. It is 21 sample size minus 1, that will be 20. 20 comma 0.005. Let's go and yes, first before we go there, 20 comma 0.005. Let's deal with this part. What is 10 divided by the square root of 21? What do you get?
2.182.
Okay.
2.182.
2.182. Then let's find the figure, the value that is here. From the T table, you get the point, because the sample size is small. Let's go to the Z. You keep this number 2.182. And so we cancel this. We go to the table and see what happens. I think the issue of going to the table is not a challenge this time around with you, right?
Yeah.
Reading a table is not a problem. A T distribution table. What's the degree of freedom? It's 20, right?
Oh, yeah, it's 20
The degree
now.
of freedom is 20, yeah. Then it's 0.05. It's here, so the critical value is 2.845. So x bar is 17, right? We're creating the range. So it's 17 plus or minus 2.845 multiplied by what is the critical value that we found for last question?
2.182.
2.182. Then you create the confidence interval. Very easy. What's the interval? Upper limit. What's the upper limit? 17 plus this will be, first of all, find the standard error, so the margin of error. What's the margin of is what?
0.845.
No, it can't. 2.845. Oh, okay. I thought you were saying that's the answer.
No,
times
no.
2.185.
Yes, 2.182. 6.20779.
0.207.
6.20779.
779. Okay. So we can add to get the upper limit. Add to get the upper limit. Add to 17. Just say plus 17.
23.20779.
Then what's the lower limit? 17 minus the same number. That should be 11 point what? 11.20779, right? Is it?
It's 10 point.
It's 10?
10.79921.
Okay. 10.79921. So now look,
Yes.
this is our lower limit and our upper limit. But the mu, they say mu is equal to what? To 12.5.
12.
So just to
Yes.
check if 12.5 is within this range. If it is within this range, you fail to reject. Right?
Yes, it is within the range.
If it is within the range, you fail to reject. And what does that mean? It means that there is no what? There is no difference. Right?
Yes.
That simply means that there is no what?
No difference.
Is no difference. And the no difference in that case simply means that no difference, it simply means that that same drug is able to do what? Is able to heal given the same average, like in that same average, the average that they found here in 12 weeks. Yeah, it is. Yes, it's possible. You get the point, eh? That's what that means. Does that help?
Yes.
So basically, that is the whole idea behind all this. So when we meet in the next lecture, because this is just obvious the continuation, we will start from the chi-square, because I've talked about what have I talked about mainly? Mainly I've just talked about the confidence interval method. Then I will bring to light the idea behind the chi-square, so that you understand how we use the chi-square as well to test the hypothesis. Right.
Okay.
We can end here unless there are questions. Let's end.